Thank you for inviting me to Q2B. Koshiba from JSR. So I've been in the semiconductor industry for many years. And Moore's law, how long is it going to continue? That's what I've been working on. And I started to take interest in quantum technology. And what I want to explain to you today, well, Dr. Ito talked about the national policy. And in that effort, I was participating in that effort. And to be honest, the quantum world, we have physics people, mathematicians, and also people from electronics companies, and so expert meetings are mainly staffed by such people. But we just heard from IBM. So looking at the current situation, I think we're starting to enter a different stage. And so today, I'd like to talk about the quantum computers or the quantum effect. That's a means and not the aim. So how to change the world with this is what we should be focusing on. So we in the industry, well, we want to make or change the world. So from that perspective, I'd like to talk about the quantum technologies. So there is this law of accelerated returns. So lower left, you see the printing press. 1460 was invented, and with that, the Bible was disseminated, and the world was changed, and writing became popular. And then you have the steam engine in the middle. That was invented, and there was the first industrial revolution. Upper left, this would be around 1900s. Electricity was invented or discovered, and the second industrial revolution. So internal combustion engine was introduced, and so energy revolution progressed as a result of that. And upper right, you see, well, you see the PC and the internet from the middle of 1980s. So that would be about 75, 80 years after the second industrial revolution. We saw another major revolution there. So 300 years, 150 years, 80 years between these revolutions. So the evolution of humankind is accelerating each time. So 1985, add 40 years to that, that's 2025. So as was shown in the roadmap, probably quantum computing may achieve quantum advantage in 2025. And in the industry, companies, I think we're looking at once in a career change, and we want to capitalize on that. That's how we view these developments. It's not just about quantum computers. 5G, it took about 100 trillion yen infrastructure investment for it to be disseminated. And I think it will be around 2024 where it will be widespread in the world. And now you may think that you can access the internet anywhere in the world, but not so in the middle of the ocean. And what's talked about recently is the satellite constellations, so that the entire globe is covered by satellites, and that should be realized around 2024. Genomic analysis cost, it's about $1,000 now, could be $100, $200. So 2025 is a time when there's going to be huge change in society. And you add 20 to that, and that's 2045. Could be singularity. I think that may be possible, and you can decide whether to believe in that or not. So this, well, we talk about productivity. This is Piketty's equation, and it's based on that. G is labor productivity. R is capital or productivity. So labor productivity, that would be 2 or 3% in terms of GDP growth. Now, capital productivity in our world, that's the WACC, weighted average capital cost in our world. So be a little less than 7. In our company, it's 6.7%. So R is larger. So the more capital you have, you are advanced. So this is Piketty's formula. And B, this is bit productivity. Now, Moore's law is an economic law. It's not a technology law. So in 2 years, every 2 years, you have doubling of performance of semiconductor. Doubling every 2 years means 40% growth per annum. You know, AWS and Azure, I think you use them. Take a look. So you look at the Amazon's business results. AWS annual growth is 40%. So that means that the Moore's law, well, the amount of the number of transistors you can buy in 2 years is going to double, and they're just simply selling those bits. So bit productivity is quite high, is what you can see from this. So if you sell those bits cleverly, and if you become an AI company using these bits, you are a growth company. So from 2012 to 2015, Japan was behind in riding that wave. Now Q, this is quantum bit productivity. So semiconductors, I said, is an economic rule. So people talk about 5 to 3 nanometer. So 3 nanometer factory or fab, making that costs 1 to 1.2 trillion yen. And to cover global demand, you would need about 5 of them. That's 6 trillion yen just for the manufacturing facility. And so it costs that much just to manufacture. And you know qubit. To have 1 qubit, you have double the performance. Of course, it's not that easy, but quantum computing, the qubit productivity is phenomenal. So qubit hasn't started yet, but how are you going to incorporate the qubit productivity? Well, in Japan, people talk about the public cloud, and to do various calculations, you use the public cloud. I think you use it. Japanese companies, Japanese government, they're paying about 2 trillion yen per annum for that. It's a simple calculation, but if you have quantum computer, or if you have a qubit or quantum data center, the quantum computer cost is on average about $3,000. So if you calculate that, by 2025 or 26, the amount to be paid by Japanese companies for that would be about 8 trillion yen. So we're importing about 6.7 trillion crude oil. Similar cost for LNG. We don't have minerals, so that's inevitable. But the qubit, are we going to rely on overseas cloud? For the growth of Japan, we really need to incorporate the productivity of qubit into Japanese industry. That's what I'm thinking about. Now, Industrial Revolution had 3 essential elements: energy, communications, and logistics. So that's what happened in various revolutions. Energy, easy to understand. And so if you look at this from this perspective, one thing that hasn't been mentioned yet, a quantum advantage, if that is going to be achieved, well, there was talk about IBM Q, and we have the molecular dynamic calculations. So these kinds of specific calculations that can be done faster, but you can move on to bigger social issues from those specific calculations. This is McKinsey report. If you're if you're interested, you can Google it, biorevolution, and you can see it. And there's a URL there. Quite simply, 60% of the world's physical inputs could be replaced by synthetic biology, and I believe this. And of that, 1/3, well, you can replace steel with wood. So Sumitomo is demonstrating a high-rise building with lumber. Why is it possible? Well, there's a development in the lumber engineering, and also the structural simulation using computers, that's contributing to this. So computer technology is advancing, and that's making this possible. So what's the remaining 2/3? That's manufacturing using biotechnology. So quantum effect in the 20th century was considered to be a very special, unique effect. But as you know, quantum effect is everywhere around us. So bamboo shoots can grow 1 meter overnight. So they're taking the CO2 in the air, they're capturing that, DAC, direct capture. And with photosynthesis, they're changing that to cellulose. So they're fixing the CO2. And this bird, they can travel 3,000 kilometers. They have this little brain, and they have a sensor in it. They can sense the geomagnetism and travel. And so there is a quantum effect being used in the world of biology by living organisms. So using quantum effect in computing for encryption, for communication, and for manufacturing. In that regard, biology is a quite interesting area. And this is a bacteria that's been developed by a Japanese company. So it's gene altered, and you make it eat CO2. Then from alcohol, or you can have alcohol, fuel, all kinds of things. So this absorbs 65 times CO2 than sugarcane, produces 35 times more sugar. The point being that gene modification technology is the key. Another thing that's been mentioned, carbon neutrality. Now, apparel is actually applying a lot of pressure on the global environment. So apparel industry for carbon neutrality, I think, is going to be crucial. So of the CO2, 10% comes from the apparel industry. So 40% uses synthetic fiber, 20% organic, like cashmere. And in Europe, they're talking about no animals in the most advanced brands. So cashmere, they are trying to make it from biosynthesized protein. And so that kind of replacement is going on. You might have heard of the company Spiber in Japan. So people think they make spider web threads. So they've caught more than 1,000 different types of spiders, and they looked at the DNA of spiders and the spider web that they create, and look at the protein structure of the webs and the mechanical characteristics. And based on that database, they can freely can make cashmere or the fur of polar bear or very strong spider thread that can repel bullets. So this is bioinformatics technology. And in the apparel industry, the remaining 40%, that's cotton. I think many of you wear cotton. So cotton is very good for underwear, but for outerwear, the it's difficult to stain, and so usually chemical or synthetic fiber is mixed. And to replace that, bacteria-based fiber can be used based on protein. It's still too expensive, 50,000 yen for a parka. But if you use that, well, first you start with reuse, and then you have recycle. And the final stage is, well, with the synthetic fiber, you're burning it. But the protein-based fiber, you can cut it up and break it down with enzymes, make it amino acid, make it into glucose. Once again, feed it to bacteria. Then you can have protein fiber. So that's the cradle-to-cradle circular economy realized. What will be important there is the enzyme decomposition, how to increase the efficiency of that. So with there's the OLED molecule that was mentioned. So if you set the problem simply, then I think that it will be relatively easy to design enzymes. And also, when making various bacteria, the point will be the gene modification. So that's a world of combination optimization. If you're able to do that, then the aforementioned manufacturing using biotechnology will be possible, and that will help to reduce imports of oil. And even if you emit CO2, you can capture the CO2, feed it to bacteria again. And so you have economic security and biology, that the reactions take place between 30 to 50 degrees, so it's low energy. So the world going forward, qubit, bit neurons, those are going to be the key. And with CPUs, GPUs, and quantum computing, I think we can change the world. And I really think that in the past, electricity was powerful, that allowed communications. Then went to electronics. And so the world of electronics was born. So in one sense, energy efficiency was improved. But from this point on, are we going to go back to renewable energy, photovoltaic energy, with a lower energy density? I don't think so. I think the world going forward is going to move from electricity to electronics, to electrons, and then to quantum. So maybe you can have a nuclear fusion. And I think with quantum computing, with advanced simulation, nuclear fusion may become possible to create a new world. So the 21st century world is finally starting to emerge, I think. And toward 2040 or 2050, those people who will support those ages, those people in the 30s and 40s, we want to create the infrastructure that will allow them to utilize quantum computers. So I would like to work with the government and various partners so that you may be successful in that world. Thank you very much.